Okay, we're going to go through time-distance graphs, which could be very confusing to look at. So we're going to try to uh, show what it would look like in real life and how the graphing of this kind of works. So this will be our very first example. We're going to go through quite a few examples. There's many different words we're going to use to describe things, okay? First of all, our up and down axis, which is usually known as the y-axis, is going to measure distance, okay? Where our x-axis, which is our horizontal, is going to measure time. And for all of our graphs, this is going to be the case. Time is our independent variable, distance being dependent, right? The further I am to a wall or to a soccer field does not affect time. Just my time affects how fast I can move to it. So, this point here, it's usually known as the origin on graphs. It starts at 0. But I haven't actually written, and I'm not going to write any increments or any numbers. Okay? But we do know from working with graphs, if I'm starting here at 0, the farther I go up, what happens to the numbers on this line? Yeah, the numbers grow larger. So in other words, the distance is larger. Okay? The higher these we go up this graph, the larger the numbers get, therefore the larger the distance. Okay? Same if we're moving to the right. I start at 0. As I move to the right, the numbers grow larger, therefore time grows larger, or longer is usually a better description of it. So, without actually drawing any numbers, I'm going to describe somebody walking from a wall. Okay? So we have a guy. I don't know why that's so funny. Just some random guy here. Okay? This is our happy guy.
Give him a hat.
Does he need a hat? You think so? Okay. We're gonna have to use this guy several times. So, I'm gonna break this graph into 4 sections. Okay? I'm gonna call this section A, this section B, C, D, and I lied, E. So I guess it's actually more. No, it's still 4 sections. Okay? I've broken it this way because between those points, it's pretty constant whatever has happened. Okay? It's not changing between these points. So I have 4 different movements here. So 0 in terms of distance. If our guy here is at the wall, so I'm going to grab him, okay, and we're talking about reference to this wall here. This is our wall. If he's 0, maybe it's meters, centimeters, it doesn't matter the measurement. If he's 0 meters from the wall, where is he? Is he far from the wall or close to the wall? Yeah, he's essentially touching the wall. Okay, so our guy is touching the wall at the beginning of this. He then starts to walk. Okay? Is he getting closer or is he moving farther from the wall? Yeah, he's slowly moving farther from the wall. So we take our guy and he slowly moves farther from the wall. So this is our first movement. I'm just going to use arrows to represent it. Okay? So he slowly moves farther from the wall. And then from point B to point C, what's happening? Yeah, he's moving farther, but is he going the same pace? What has happened? It's gone faster. So maybe I should use colors to represent this. We'll use blue as a slower value. Okay. And now he's decided to move faster from the wall. Okay, so I tried to move him quicker. So now we use red. He's now moved quicker from his distance from the wall. Then, what happens from C to D? He stayed. This is constant. His distance hasn't changed. Okay? So, I'm going to write our letters to help us out here. This was from A to B. This is from B to C. From C to D, we'll use purple to represent it. He just stayed here. He didn't go anywhere. And then from D to E, he moved back to the wall. Was it slow or would you say it was quick? It was pretty quick. It almost looks like he moved right back to that spot. So we'll do it red, just the other direction. He moved quickly back to the wall from D to E. This guy clearly doesn't know where he's going. He's very lost. Okay? But that is how we describe time-distance graphs. So if you notice, he actually never moved left and right on this wall here. Even though sometimes it gets confusing, we think of this going to the right, to the left. This is measuring time. Time continues no matter what he's doing. So whether he decides to slowly walk, then pick up speed and wait, and then slowly walk back, time continues. It doesn't matter if he stands still, time continues to pass. And that's where this point is here. Okay? So using this same idea, we're going to try to describe this one. Again, we know that this is our distance and this is our time. This being 0, again from the wall. Where is he starting?
Far away.
Yeah, he starts far away. So we just got to estimate. He's far away. And what does he do?
He gets closer and closer.
Yeah, so we'll say he walks to the wall. And it's probably not that quick. We better label it A to B. Okay. So he slowly walks to the wall. I should write those letters there. This is our AB movement. So he slowly walks to the wall. And then from B to C, what does he do? He stays. So from B, C, he just stays put. He just waits there. So essentially, if we were to show this over time, this is what's happening. From A to B, he's walking to the wall. And then from B to C, he stands there and waits. Maybe he's ordering something or doesn't know what to order. Okay? So let's go to our next example here. It's very similar to the one before. Okay? Let me get our guy here. Bring him down. So here's our lovely guy. Where does he start? Nice. Yeah, far from the wall, right? And then what does he do from A to B? Is he going towards the wall or away from the wall? Yeah, he quickly moves towards the wall. Okay, so he goes and he sprints to the wall, or at least to the spot he's at. And then from B to C, what does he do? Just stands there. So he ran somewhere and then he maybe decided he was going the wrong way, doesn't know where to go. Okay? But that's just the idea here. So even though we only used one line to represent this, in terms of what was actually happening, he quickly sprinted here and then waited. Again, because it's referring to time, he quickly sprints and then he waits. Okay? So this is constant. Okay? This is decrease in distance. Before we had an increase in distance, and this is a constant distance. Okay? And finally, there are two more I want to do. So let's quickly go through these and then I'll take up all your questions. Okay?
What if it was a beep test? How would it look?
Go back and forth and back and forth. Okay, so let's make one if it was a beep test, okay? Let's do this one, and then the last one I'm going to change into a beep test. So, in this one, there really isn't distinct linear relationships. It's kind of a curved line. So I'll call this A to B. It's kind of hard. Oh, I better get our guy again. Okay. Think about it as we scroll down. What is happening with that curved line? First of all, where does he start? He starts far from the wall, and then what does he do?
Gradually gets slower.
Yeah, but at the very beginning, what would you describe this as? Very fast. Faster than wherever before. And maybe we could split it like that. Instead of calling that B, let's call this our B, and maybe this will be our C. Okay, so he quickly sprints, and then he's slowly, is it constant? No, he's slowly getting closer and closer to the wall. So, here's our AB, and then our BC kind of described like this. So, he sprints quickly to the wall and then slowly starts walking to the wall. And he's probably going to get closer and closer, and it goes slower and slower. Okay, so that's the idea here. Now, let's say this guy was doing a beep test. So, we're going to create the graph this time. Okay, let's create this graph.
It will just go up and down, make a lot of triangles.
You're right. That's exactly what it's going to do. So here's our distance and here's our time, and we'll say he's in reference to the wall, so let's get our little guy here. Bring him down. Okay, so on a beep test, what do you normally do? You start where? At the wall. Where would that be on this graph in terms of distance? Would it be way at the top of the arrow or? 0, that's right. So it starts at 0. Okay? And if you guys remember with those beep tests, what happens with time?
It gets faster.
It gets faster and faster. So, let's say the first one, he jogs his way out here. Okay? Maybe it's a constant pace. So he slowly jogs away from the wall. Then what happens in the beep test?
Beep, and you go back.
Okay, and then you go back. Okay, so that's our A to B. And then he has to turn around and come back to the wall. A little bit faster, right? So this one would be a little steeper than before. He comes back to the wall. That would be maybe our BC. And I'm just going to use red because we're going to go on the assumption that it's a relatively quick pace. Okay. Then time picks up again. He's got to run away from the wall faster than before. So the line gets even steeper than it was before. Okay, that's going to be our A, B, C, C, D. So here's our C to D. Faster he moves away. And then what happens again? He's got to run back to the wall. It gets even faster. And then eventually would pick up this type of idea. And then what happens if I end it there? Go there, and then he gave up. Okay? We'll say he passed out, he gave up. That's it. Just lay down on the ground there. So there's his beat test.
So what do you do on your beat test?